recently on StarTalk, Neil deGrasse Tyson and one of my favorite physicists, Sean Carroll, got on and they talked about quantum entanglement. They had a really interesting discussion, 9-10 minutes long. And I wanted to just do a little bit of a react and talk about sort of these concepts that relate to quantum mechanics, quantum computers, and kind of bring that all around to this conversation we're having here on the channel about quantum computers and the future of those. So let's jump right in. All right, guys, so I have the video pulled up here. I'm gonna grab my headphones and we're gonna get going. All right, let's listen to this conversation.
Entangled particles.
Well, this is part of this fact that we said before, that there's not a separate quantum wave function for every individual thing in the universe. There's only one wave function for all of them at once. And what the wave function tells us is the probability of observing something. So if you have two particles, and let's say they have positions, you don't know where it is. In fact, literally, when something like the Higgs boson decays into an electron and a positron, the anti-electron. And you say, well, what direction are they going in? And the answer is they're both going in all directions. Their wave functions are coming out sort of in a spherical pattern. But then when you observe one of them,
that's where it is.
That's where it is, and momentum is conserved. So now you know the other one is going in exactly. So you know where the other one is without having detected it yet. That's entanglement.
So what entangles them?
The rules of physics.
Okay, that doesn't. That's not. Stop it.
That's just the end of this interview.
You can't do
Get
that.
him out of here.
That's my mother saying because I said so. That's what that. Mom, why can't I have ice cream for breakfast? Because I said so. That's why.
What law of physics prescribes this?
Quantum mechanics. That's the nature of quantum mechanics. It's sort of that. This is how science works. You sort of conjecture an idea, then you say, is that right or not? And so in quantum mechanics, the fundamental way things work is that the state of the universe is a vector in Hilbert space, which means that the combined state of every particle in the universe and every field and everything is described by one single mathematical object. And in fact, I don't like the word entanglement because it kind of it makes it hard to update your intuition. It makes it sound like what really exists are these two particles, and you measure one, and then you're like, why did the other one change? If you just accept that what exists is the combined quantum state of everything in the universe, then it's no surprise at all that when you look at a little bit of it, it affects the rest.
Okay, but
So right off the bat, a couple things. One is observation, right? So they're talking about this thought experiment, one of the most famous thought experiments with Schrödinger's cat, which the cat is both alive and dead simultaneously when it's left in a box. And I really like how they talk through this, that there are multiple realities possible, but only when observation happens does one of those realities come into existence.
Interesting.
Can I just take two random particles that were not born together and entangle them?
Sure.
Okay.
Yeah. Entanglement happens whenever you have two objects that are not entangled, but they interact with each other in different ways depending on different parts of their wave function. So let me just give you a down-to-earth example. Right. Schrödinger's cat.
Right.
You've heard about this. Schrödinger, who apparently didn't like cats, goes to a great amount of thought experiment effort to put a cat in a superposition.
That's right. That would have never worked with Schrodinger's dog.
No.
That would not have flown.
Schrodinger's daughter
people wouldn't have had it.
Said that he didn't like cats.
Right.
Okay.
This is why he picked the cat. So it's in a superposition of alive and dead. I'm a cat person. So in my version, they're a superposition of awake and asleep.
Oh,
it's very sweet. You don't have to kill the cat.
You don't have to kill it.
I didn't know you didn't have to kill the cat.
The point is, you don't have to kill the cat, but the point is they're different places in the box, okay? And what that means is that everything in the box, the air, the light, everything moving around in the background interacts differently with the awake cat running around trying to get out and the asleep cat just snoring peacefully on the ground. And so the environment, as we say, entangles with the cat right away because it interacts with it, but interacts with it differently depending on different parts of the wave function.
Okay, I don't know that that's more clear to me. So you're sleep and awake cat, but we declared that without actually sticking a sleep and awake cat in the box. I mean, we're just asserting that.
Right.
Why does that make
could
it?
the cat just be drowsy?
In between?
No, this is Schrodinger's whole point. This is why he set up in the experiment. There's a radioactive thought experiment. He didn't
Just
do
to
it.
be clear.
So radioactivity, and there's a Geiger counter, and the Geiger counter will click when it detects radioactive decay.
In radioactivity, you have no idea which particle is going to decay.
Okay.
Just statistically, you know very accurately what fraction of them will. But the fact that you don't know creates a brilliant, beautiful, random number in a sense.
Yeah.
Okay.
Quick pause here. If you want to learn more about quantum randomness, head over to my channel and let's take a look at. So I have a video here. Let's see. It's called Pseudo-random versus quantum random. So they're kind of touching on this concept that it's very difficult with modern computers. In fact, it's impossible with the modern computer to have true random because you need a seed, and the seed is predictable, and therefore it is not random. So go take a look at this pseudo-random versus quantum random. It's a breakdown of this concept. And in terms of this conversation, he's talking about how radioactive decay isn't by nature predictable. So therefore it is random. But when I watched this the first time, I thought, even if radioactive decay is following some sort of laws of the universe, we may not know what those laws are at this point in time in human history, then even those are predictable. So quantum computing and what they're doing with quantum computing now, recently, like this year, 2025, 2024, we can actually get true random.
So if you needed a random thing, you get a decaying set of particles, and you can draw randomness from that. That is that's as good a random as we can produce.
100% random as far as we know.
Except for
Nothing
Okay.
better. And this is, the 1930s when Schrödinger was very unhappy with the state of quantum mechanics. He was not bragging about quantum mechanics. He was saying, surely you don't believe this. And he says, when we say this particle has a probability of decaying, what quantum mechanics actually says is there's a wave function for the particle, and it is in a superposition of I have decayed and I have not decayed. And the part of it that is decayed sets off the Geiger counter. So now the Geiger counter is in a superposition of I have clicked and I have not clicked. And the Geiger counter in the part that clicks knocks over a hammer, breaks a vial full of sleeping gas, and the cat goes to sleep. So the cat goes into a superposition of being awake and being asleep. That's the whole point of the sort of Rube Goldberg gizmo that Schrödinger builds in there.
But how does that help anything?
Well, Schrödinger's trying to say, in the way that we thought of quantum mechanics back then, there was these giant debates between Bohr and Einstein about what quantum mechanics really means.
Niels Bohr.
And Niels Bohr would have said, look, when you open the box and look, the cat suddenly changes from being in a superposition of awake and asleep to being one or the other.
Okay.
And Schrödinger's like, come on.
Right.
You think
He's
that when I
saying,
look
no,
at it,
right.
it changes like that?
I got you. So his thing is that superposition exists at all times, everywhere, no matter what. And it has nothing to do with the fact that I looked at it. It's in that superposition. You just got to accept that.
He should have said that. He blinked. He lost courage at the last second.
Oh.
And it was a decade and a half later, or 2 decades later, a graduate student at Princeton named Hugh Everett said exactly those words. He said, just believe what the formula is telling you. And what the formula tells you is when you look at it, guess what? You enter into a superposition.
Right.
There's a part of you that has seen the cat awake and a part of you that has seen the cat asleep. And Hugh Everett says that's because both of those possibilities exist just in 2 separate worlds.
Because what we're dealing with is a probability in the first place. Yeah. So that always exists. It doesn't change because you observed it.
Exactly.
It's still the same.
Who cares?
Well,
That's
right. You just mentioned in that world.
So before you ask this question, if you're interested in learning more about this, I built the quantumbull.com and I have a whole learn page that covers some of the basic concepts of quantum computing. What is it? Why should we care? What do you need to know? And one of the topics covered is the Schrödinger's cat. So the task is not so much to see what no one has yet seen, but to think about what nobody has yet thought about, which everybody sees, is one of the quotes from Schrödinger himself. And if we look at kind of this concept of observation as the cornerstone, right? So these things are happening all simultaneously, but when we observe them, then the wave function collapses, forcing it to adopt a specific state. And we can actually see that in experiments like this light slit experiment. And I have that, I think, here on the Learn page. So if you want to learn about the light slit experiment, go check out this page. Google's quantum AI is mind-blowing.
I have some memory that I haven't heard about lately, but the Copenhagen interpretation.
Yeah, that was Niels Bohr.
Niels Bohr is Danish.
Okay.
And so they credited, I guess, the city, but it was really a Bohr interpretation, not a Copenhagen.
Well, he had his people who would come into his institute and hang around and go out, spreading the gospel of Bohr.
Oh, gosh.
So this was the idea. Yeah, Heisenberg, Pauli, there's a bunch.
Okay, yeah. So can you catch us up on the many worlds interpretation?
Right. So the Copenhagen interpretation really frustrated people like Einstein and Schrödinger because it seemed to give up on arguably the single most crucial feature of science, which is realism about the physical world. Before quantum mechanics came along, you knew there was a real world out there, even if you didn't know exactly what it was doing.
Measure it.
Right. And Bohr and his friends seemed to be saying that before you open the box and look at the cat, there is no fact of the matter about what the cat is. And Einstein and Schrödinger said, even if you don't know what the fact of the matter is, there should be some. Right. And so Everett sort of lives up to the dreams of Einstein and Schrödinger and says, yes, there is a reality there, but sadly for you, the reality is there's many different worlds and they don't interact with each other. So Everett is just saying that in this world of superpositions that quantum mechanics always describes, you should just take them all seriously. They're all actually there. It's not just a mathematical trick.
That is really, really tough.
I get it.
That is rough.
All right. Well, you got the sleepy cat, you got the awake, sleep cat, you got the awake cat. Is there a world where I open the box and I see the awake cat as a different world from the one in which I open the box and it's asleep?
There will be two worlds, and it happens long before you open the box, because as soon as the other stuff in the box, as soon as the photons and the atoms and everything become entangled with the cat, boom, there's two worlds.
So where are those two worlds? Or is that the wrong question?
That's the wrong question. I see that you quickly got it. As soon as you asked it, you knew.
No, I knew. But
the worlds are not located in space. Space is located in each world.
Holy gosh.
He knows it. Chuck gets it. He gets it.
I gotta leave.
I need you, Chuck. No. Chuck, I need you for
I don't
this.
believe anything anymore. It's over. No, there is no God. Oh, no.
Chuck, I need you.
That's also true. But okay, that's a whole nother podcast.
Okay. So very funny. And also, I think we're supposed to struggle with these concepts a little bit, right? So when we think about these concepts like Schrödinger as a cat or entanglement or observation, we're really talking about things that we are still discovering and we don't fully understand. We're really on the frontier of science and we're on the frontier of our understanding. So we have theories and we have basic understanding or theories about how these things work. it's difficult to prove. The light slit experiment is one experiment that really shows kind of that observation as a cornerstone for the quantum wave function. So take a look at that video that I pointed out, and head over to thequantumbull.com/learn if you're interested in learning more about quantum mechanics, quantum computers. And if you're interested in coverage like this, there's also great opportunities right now. We're on the precipice of a new world order where quantum computers will become more and more powerful. And a lot of these principles that we are starting to learn and understand and actually begin to do compute through and manipulate quantum computers for whatever purposes we have, we're right on the cusp of all of that. So it's a really cool time to keep learning and educating yourself, and I encourage you to do so. That's all I got for you. If you took value out of this, please consider leaving a like or subscribe. Have a great weekend.